Afternoon, Year 11. So this is your revision PowerPoint for the topic we're just coming to the end of. Apologies to those of you who tried to watch this video yesterday. The sound didn't work and I'm not entirely sure why. But this is going to take about 10 minutes and it will cover everything you need to revise for next week. Okay, electrical power is our topic. Electrical power is a very useful thing that we have in modern life, and we're going to see why it's so useful, and we're going to be able to do some calculations to do with it. Right, the first thing you need to know about is energy transfers. Electrical power is really useful. In the olden days, in order to get a source of energy into your home, you used to have to lug in a massive great bag of coal or logs or something to get your energy source in there. But nowadays, we can have electricity delivered to our homes, and energy comes right into our homes without us having to carry anything heavy. And not only that, when that form of energy is in our homes, we can turn it into all different kinds of energy. It can do lots of different energy transfers. So imagine a toaster, you've got your electrical energy going in, but of course you've got heat coming out. Very useful energy transfer. A torch, electrical goes in and light comes out. Another useful energy transfer, but a different form at the end. Nowadays you've got modern cars. Okay, so you can have an electrical car which you charge up at home, and I guess the ultimate aim of that is to get some kinetic energy out of it. So yet another different energy transfer that electricity can do. So it's very, very useful in that sense. So we know a little bit about the energy transfers involved with electricity. Of course, in some of these cases, it's not just going to be light energy you get out. Sometimes you'll get a bit of wasted energy, such as heat. Torches can warm up when you use them too much. Cars can heat up as well. They might also make a bit of a racket, so there'll be some sound energy wasted. Now in this case, this is wasted energy. It's not what you want it in, and it means that some of these appliances that are doing these transfers are not going to be 100% efficient. In fact, I don't think you'll ever find a 100% efficient appliance, except for maybe a heater, because most energy transfers ultimately end up as heat. Now efficiency is not something you just need to know the definition of, you also need to be able to know how to work it out. But you don't actually have to remember anything, because you'll be given an equation sheet that's got this on it. So just make sure you're comfortable with that, and you'll be able to do all of the calculation questions to do with this particular area of the topic. So let's focus on this equation here. I'm going to give you an example, and what we're going to do is we're not just going to use this to do the sum, we're going to rearrange it, because that's what you've got to do at a higher tier. So for example, if we go back to our toaster, let's say that this device here transfers 1,000 joules of energy. Okay, and it is 70% efficient. What I want to know is, how much heat am I getting out? So look at this. We've been told the efficiency, I told you it was 70%. We know that the total input energy is 1,000 joules. What we don't know is that useful energy up there. Now some of you have already done it in your head because I've used nice round figures, but I'm still going to go through the method so that when you get not very nice round figures, you can actually have a bulletproof method step by step to fall back on. Right, here's our equation right here, but unfortunately we ain't finding efficiency anymore. We're actually looking for this one instead. So this equation as it is not going to do the job. So we have to rearrange it. That's what higher tier students have to be able to do. So let's get our rearranging triangle handy. This, I know I keep banging on about this, but this is really useful. If you're in the exam and you have a brain snap and you suddenly draw a blank, fall back on this every time. It's simple, you can practice it, and there are some simple rules that will get you through. So we know there's a rearrangement going on. We're looking for the useful energy, but we don't know how to get there. So what you do is you take a step back and you look at that equation as it's written on the page. And what you've got is efficiency equals, and then on the right hand side you've got something over something. You've got a line in the middle dividing them. Well, look at the triangle. There's a line in the middle dividing some things over here. So we know that our useful is going to go up top. And that means that the total input has got to go down here somewhere. And it actually doesn't matter where you put it on this side or that side, but we're going to put it over here. There's only one empty space now, so the efficiency is going to go over there. Simple. Right, now comes the easy bit. You're going to use this triangle to rearrange the equation, and in order to do that, you simply hide or get rid of the thing you want to find. Now all I'm left with is efficiency on the bottom next to total input. And we know that because they're next to each other, that actually means they are multiplied together. Let's do that a bit neater. Or not, there we go. They are actually going to be multiplied together. So what you're going to have is your efficiency multiplied by the total input, which if we look at our numbers, we're going to have 70% multiplied by the total input energy. Now be warned here, there's a trap. That's a percentage. 70% multiplied by that does not give you 70,000, because 70% of course is equal to 0.7 in real terms. It's a decimal, okay? So what that means is it's going to be 0.7 multiplied by 1,000, and as many of you have guessed well in advance of me, we're going to get 700 joules of useful energy out in that example. Okay, efficiency, done. We're happy with that. Let's move on to another concept that sometimes people find tricky, electrical power. Now power, I've written here, is a measure of energy flow. And that means it's a measure of the number of joules of energy flowing through an appliance every second. If you wanted to think of a real world object to sort of visualise this, think of a hosepipe. Think of one of those whacking great hosepipes the fire service used to put out burning houses. There's going to be a lot of litres of water coming out the end of that every second. Now imagine a little wussy hosepipe you have in your garden. There's not going to be many litres of that coming out every second. Okay, so the flow is less, so it's less powerful. Bring that back to our toaster example. If you've got, let's say, 100 joules going in, coming out every second, then that means that this thing has got a power of 100 joules per second. But that is very long-winded. Joules per second. Bit of a mouthful, that. So actually they've come up with a unit that we can use instead, which is known as the watts. So that is equivalent to 100 watts. That just means the number of joules per second. Pretty straightforward. Let's do a calculation. I've got a 60 watt light bulb here, okay, and it's on for 2 hours every night. Now, looking in your equation sheet, you'll find out that the power is equal to the energy divided by the time. I want to know how much energy comes out of this light bulb in an evening when I have it on for 2 hours. So suddenly, we've got to do a bit of rearrangement. So triangle time, so we're going to have E up there, T down there, we're going to have P here. I want to know the amount of energy, so I'm looking at this one here. So if that were to disappear, I'd have P times T. So it's going to be the power multiplied by the time. Okay, that's the sum I'm going to do, but I do not do 60 multiplied by 2 because this is in hours, and I need to convert it into seconds. So first thing we do is we take our 2 hours, we multiply it by 60 to get it in minutes, which is 120. Now let's multiply that by 60 to get that in seconds, okay? And that's going to be, off the top of my head, I believe 7,200. Okay, so what we've got there is the number of seconds. Now we can do the sum straightforward. We've got the time, we've still got the power, so you do 60 multiply 7,200 and you get an enormous number. That's how many joules I have just by turning a light bulb on for 2 hours every night. I'm going to have that many joules coming out every night. Quite a large number. If I were to add up how much energy gets used in a week, or a month, or even a year, it's going to be an astronomical figure. We're going to have zeros going on forever. So when it comes to buying my electricity from the power companies, I'm not going to write down how many joules I've used. We need a much more manageable figure, because I don't want to be billed for 3.5 quadrillion joules. I want to be billed for a number I can get my head round. And that's why the power companies have come up with another measure of energy. Remember that power is equal to energy divided by time, or to put it another way, energy is equal to power multiplied by the time. What we're going to do is we're going to take this here and we're going to use it to come up with a new unit of energy. So let's take our toaster again. It's got a power of 1 kilowatt. Well, let's imagine that I switch that on for 1 hour. Okay, the amount of energy it used would be a lot of joules, or we could just say, well, I've done 1 kilowatt multiplied by 1 hour. Let's call that 1 kilowatt hour. And this is the unit in which we purchase electricity, kilowatt hours. Hopefully, that's all making sense or sounding at least moderately familiar. So if we have a look at what I set out to do, we've had a good look at power, and we're talking about the cost of electricity now. Once you can work out the number of kilowatt hours you've used, you can start paying for them. And they cost somewhere in the region of 7 to 20p, depending on the exam paper you sit. They cost pennies as opposed to pounds. And so that's what we're on to next. The cost efficiency will come later on, but what we're going to do is we're going to look at an exam question that deals with both of these things. So let's find the exam paper. Here we go. Here's a house, and first thing it says down here, this is the first thing you've got to do: calculate in kilowatts the power of the heating system used to keep the inside of the house in diagram 1 at a constant temperature. Right, so let's do this. Let's actually have a go. I'm going to scroll down, hopefully make that a bit easier to do. Now, if you look around the edge of that, you'll see lots and lots of arrows that show the heat energy exiting the house. Let's just zoom out a little bit. Okay, and there are lots of different ways you can get out: through the roof, through the walls, through drafts, all that kind of stuff. And the first thing you might start to do is look at this, and you might start to panic, because look, the units are given not in watts, they're given in kilojoules per second. We haven't met kilojoules per second. What does that mean? But before you panic, we know that a joule per second is actually the same as a watt. So all this is a kilowatt. They're just trying to confuse you by changing the units. Now imagine you've got a little heating system in here supplying energy to replace all the energy that leaks out through here, here and here. What it needs to do in order to maintain a constant temperature is it needs to match all of these added up. So it's a straightforward addition, and you should find, nice round figure, that actually the heating system needs to be 5 kilowatts. Okay, that one, I reckon, pretty easy, we can do that. So now we've got a figure for how much heat energy there is in there, and how much your heating system needs to transfer in order to keep the house nice and warm. So far, so good. Part 1A done. Let's have a look at the next bit. In winter, the heating system is switched on for a total of 7 hours a day. Calculating kilowatt hours, energy transferred each day from the heating system to the inside of the house. Use the correct equation from the physics equation sheet. Little look down here reveals that this is a 2-marker question. So rather than losing a mark by just writing the answer, we're going to have to do something else. Now the second mark here is for choosing the correct equation. Right, we are calculating the energy. We've got the time, and we worked out the power on the previous page. So what we're going to do is we're going to use that the energy is equal to the power multiplied by the time to calculate this. Now in this example, we're not calculating in joules, we're going to be calculating in kilowatt hours. They've told us that down here. So we don't need to convert it into seconds and all that. We just multiply the number of kilowatts by the number of hours it's on, and you get an answer of 35. 2 marks in the bag. Last bit we're going to do. Energy costs 15p per kilowatt hour. Calculate the cost of heating the house for 1 day. Well, that's really straightforward, isn't it? We've already worked out we need to use 35 of these kilowatt hours, so it's going to be 15 multiplied by 35. My mental arithmetic is not great, but I reckon that's 525 pence. Hopefully that made sense, Year 11. You need to be revising these things, making sure you're really comfortable with them, and we'll do an assessment next week.